Hello, I will be talking today about some concordance invariants that one can derive from the Khovanov-Rozansky link homologies, or the SLN homologies. So I'll start by just going through the definition of these homologies, I guess with a particular formulation with an eye toward these invariants. And then at the end, I'll talk about kind of the most general algebraic gadget that I know of that you can use to extract this concordance information from. So to start off, I'd like to talk about the concept of a matrix factorization, which is really the essential bit of algebra that makes this whole story tick. So a matrix factorization is just like a chain complex, except instead of requiring that the differential square to 0, we require that it square to some particular element of the ground ring. And now that this requires a couple of changes. First of all, sort of the homological grading on a matrix factorization now can't be a z grading anymore, because otherwise d squared would change that grading. And if a ground ring is going to be supported in homological grading 0, that can't be the case. We only require z mod 2z grading. And I guess at first it seems like you can't do a whole lot with this, because you couldn't, say, take its homology, you couldn't do anything like that. But there are a number of useful properties that make this act a lot more like a chain complex than one might expect. So first of all, if you take a tensor product of two matrix factorizations, with two different potentials, you add together the potentials. And to make this work out precisely, you need to sort of define the differential with the appropriate signs on the tensor product to make cross terms cancel out. But that just uses z mod 2 grading, z mod 2z grading I talked about earlier. And similarly, if you take a Hom space between two matrix factorizations, you take the difference of the two potentials. And what this means is if you have two factorizations of the same potential, so if W1 equals W2, then we have a chain complex of maps between them. And this really gets the theory off the ground, right? Because we can say that a chain map of matrix factorizations is just a class in this chain complex whose differential is 0. So concretely, that just means that like a homomorphism, a chain map, say f from M1 to M2, is just a map f with the property that like f d1 equals d2f, because the differential in this chain complex is taking commutators with the differentials of M1 and M2. But this also automatically gives us a notion of homotopies of two such chain maps, because this f is a cycle in a particular chain complex. We say that two such maps are homotopic if they represent the same homology class. And that lets us talk about homotopy equivalences of matrix factorizations and all those nice things we want to be able to do with the chain complex. So if you like, we have for a fixed potential W, we have a DG category of matrix factorizations of W. Okay, so some important examples that will kind of follow through the entire time we're talking today of these matrix factorizations are, first of all, if you just have a pair of elements in your ground ring, you can form a factorization of their products. This is really just an ordinary factorization because everything is one-dimensional. So by this notation here, whenever I sort of draw a diagram where an arrow goes off to the side like this, I mean it wraps around, because it gets kind of messy if you have to keep drawing sort of arrows going back. But this is really what this is, sort of A, B, and then in the z mod 2 grading, like this one is in degree 0 and this one is in degree 1. So this is a matrix factorization with potential A times B. And then you can take a tensor product of a lot of these together and get a matrix factorization of sort of the sum of a bunch of products of two elements of your ground ring. So these are what are called a Kossel matrix factorization by simple analogy with the context of a Kossel complex. Okay, and then finally, sort of the most critical example here is if you have any sort of polynomial in one variable. There's a matrix factorization of the polynomial, so that this one has potential W of y minus w of x. I guess there I wrote y to the n. I should probably write w of y minus w of x, although in lots of examples w will just be a monomial. So this is a matrix factorization with that potential, and it sort of plays a very important role because it's sort of the identity or a change of variable factorization under the tensor product. And what we mean is if you start with any matrix factorization of W over a polynomial in one variable, we can form this tensor product. So what I really mean is perhaps first extend scalars from M from Q and X to Q and XY, and then take the tensor product. And the result of this will be a factorization of W of X minus W of X plus W of Y equals W of Y over Q and join X, Y. So if you take that tensor product and sort of just restrict scalars down to just a single variable polynomial in Q adjoin Y, what's left is actually essentially homotopy equivalent to the M you started with. I guess after sort of replacing all the X's you had in M with Y's. So that's the sense in which this I is the identity under tensor product. And there's a nice graphical language here. If we draw M sort of like this, with a single thing coming out labeled X, what would this just mean? A matrix factorization whose potential is W of X. Then we can draw IXY as just an arc with the two ends labeled X and Y, and the tensor product over Q adjoin X just corresponds to gluing along the X's. So this, we get this, and we remember the X here, but we also have a Y off here. And then restricting scalars just corresponds to erasing the X. And we're left with the change of variables. And one last thing I want to say is what happens when you take the tensor product like this, when you take, there we go, Y of X, Y tensor I, Y, X. So in the graphical language, this corresponds to a circle. Well, this turns out to be the Kosovo complex 0 W prime of X. Now, this is an honest chain complex, which you could think of as being because this circle we've drawn has no boundary. And the homology of this chain complex is just going to be Q adjoin X modulo W prime of X. And in the knot homology, the Khovanov-Rozansky knot homology we'll talk about soon, this will be what we assign to the unknot. So sort of we want to an arc of the crossing of any knot diagram assign this factorization IXY, and then we need to figure out what we want to assign to the crossing, and then we'll have a knot invariant. Okay, and then the final sort of very key example that we're going to need here is if we suppose that instead of just factoring into two terms, we have a potential that factors as a product of three elements of our ground ring, then we can form three separate Kosovo matrix factorizations. We can call them MA, MB, and MC, just in terms of the three ways to bracket that three element product into two elements. And with this setup, there's sort of chain maps between them. So what I have drawn in the diagram down there, well, this is just a copy of MA, and this is just a copy of MB. And we have some chain map here. You can see that those, where again, I'm using the convention that when I go off the edge of the page, I wrap around to the front edge. But by symmetry, so we had a map from MA to MB, we get maps from MB back to MA and similar maps between MB and MC and A and MC. So that's drawn here. We sort of have this triangle. And the important fact about this is it's essentially an exact triangle going around either way. So if you take two steps along, you get something that's null homotopic, which you can see because I guess it's not completely obvious, but you see you do something A to BC to BC, and then if you go from this to B AC and this back to A, say to C AB, this one is going to be C1 A1. So what you get in the composite is the map that's, well, you trace it through. You get multiplication by C up here, and multiplication by A down here, and that's null homotopic because your homotopy goes something like this. It's like a copy of 1 here. Okay. So this is, and I guess I should also say that this is also sometimes important that when you sort of go forward and then back, in this case, that's multiplication by C, just on the nose, and ditto for the other ones. Like if you go between MB and MC, multiplication by A. And then finally, the mapping cone of any one of these maps is homotopy equivalent to the third. So MC, say, is homotopy equivalent to a mapping cone from MA to MB, and also to a mapping cone from MB to MA. So we sort of have like an ambidextrous decomposition into two parts. Okay, so in the particular example, there's a particular example of that general pattern that's going to be relevant here, is over this quotient of a polynomial ring. Now you could not take this quotient, and actually in the original paper, Khovanov-Rozansky don't take this quotient. It makes the factorization a little bit more complicated though, because what you assign to one crossing now has to have larger rank. You sort of have to impose this relation in your differential instead of putting it in by hand. And putting this in does cause a little bit of an annoyance further on when we want to define, say, a reduced homology, but for now it makes things much simpler. So we're going to impose this relation that I guess was first put in sort of Rasmussen's formulation of this setup. And now the important thing is with this relation imposed, that if you add together any just W from here and going forward is just some fixed polynomial in one variable. If you take W of x0 and plus W of x1 minus W of y0 minus W of y1, this is divisible by x0 minus y0. Because if you also impose the relation x0 equals y0, then this relation on the sum of all of them says that also x1 equals y1, and certainly if x0 equals y0 and x1 equals y1, this whole business is 0. But the same story proves that this is divisible by x0 minus y1. So we can decompose it into these two factors, these two linear factors, and then something else. I'll call W0 for now. So we're in the story we had before with this being A, this being B, and this being C. So now this Kossel complex with x0 minus x1, we want to think of as being a virtual crossing. x0, x1, y0, y1. Because in the differential, we have x0 minus y1, so we're imposing x equals y1, and then we also had this extra x1 minus y0 from again, that relation we imposed. So what this is saying is that we can express this as a mapping cone of, right, so similarly, we have that one just corresponds to a pair of vertical arcs that don't cross each other, this first one here. And then the second one we're going to call this like wide edge, or this two labeled edge. So we have a decomposition of this virtual crossing as a mapping cone from the resolution of the crossing to this singular resolution, say, and also one in the other direction. And this is now sort of enough to define the homology. The idea will be, okay, first I will say that in the particular case when W equals 1/3 times x cubed, you can calculate that this W0 is just equal to x0 plus y0. So what that means is before we had this double crossing as the complex W0 and then the two linear factors. This is now equal, because the W0 is equal to x0 plus y0. You can think of this as kind of being like this, because this is imposing the relation x0 equals minus y0. You have to sweat a little bit about orientations. That turns out not to be a gigantic issue, right? Because if we follow the orientations, we'd be in a bit of a trouble. And this ultimately is why Khovanov homologies, or the original SL2 Khovanov homology, as opposed to the more general SLN version, you don't need to work with this double edge. You can just work with the two resolutions of a crossing. because of this nice algebraic coincidence, it's because it's this polynomial 1/3 x cubed that is the potential in the Khovanov setting. Okay, so now to define a knot invariant, we obviously don't want to just put this virtual crossing complex at every crossing of the knot, because then via that fact that the factorization I that sort of builds up the two arcs of that virtual crossing is the unit for the tensor product, it would just unravel to be the single circle. The unknown wouldn't get anything interesting. But if we remember a bit of extra data about the mapping cone, we can keep track of a filtration on the matrix factorization and assign a filtered matrix factorization to every crossing. So for a positive crossing, we're going to take the mapping cone of the straight resolution to the singular resolution, but then put the singular resolution in filtration level 1 and put the straight resolution in filtration level 0. And then similarly for the negative crossing, we just flip the terms around and put one term in filtration level -1, another term in filtration level 0. So then starting from any knot diagram, let me just draw a quick example. Say the trefoil, we start by taking a polynomial ring with one variable for every arc of the diagram. So here we have like x0, x1, y0, y1, and z0, and z1. And then we're going to impose those same relations we imposed earlier in order to have those things in order to get the factorization we were talking about earlier at every crossing. So here we have x0 plus x1 equals y0 plus y1 equals z0 plus z1. And then just over this ring, we can kind of extend scalars from that single crossing ring to this larger entire diagram ring for every crossing and take a tensor product of those filtered matrix factorization at every crossing. And we get in the end a filtered matrix factorization corresponding to this knot diagram. And I should say that actually it has a second filtration on it. So if the polynomial W happens to be homogeneous, you can define a second grading on it. But if polynomial W started with isn't homogeneous, you can't define a second grading, but you can still look at what that grading would be if your polynomial was homogeneous of the degree the polynomial is. And then the other terms only decrease that grading. So you get a doubly filtered matrix factorization. Although it's a matrix factorization of 0, because when you take the tensor product of all of the individual crossing factorizations, all the potentials cancel out because they correspond to the endpoints of those tangles. So we get, in fact, a filtered chain complex with a doubly filtered chain complex. Okay, and then the key fact here is that if you have any concordance between knots, we have a filtered chain map between these complexes that induces an isomorphism on their overall homology group, right? So that when I say homology, I mean, like you just forget about the filtration entirely, you have a chain complex, take homology of that. And this is always going to be something that doesn't depend on the knot. I should say this is much, much, much weaker than being, say, a filtered homotopy equivalence. In fact, like you get something just about that if the knots are isotopic rather than just concordant. But it's that difference between a filtered homotopy equivalence and this just isomorphism on homology that is the difference between the isotopy information this theory holds and its concordance information. If you want to think about it in one way, we could say that concordant knots, they have homotopy equivalent chain complexes here. And the maps in that homotopy equivalence are filtered chain maps, but the homotopies might go back arbitrarily far in the filtration. So we're not going to have a filtered homotopy equivalence necessarily. Okay, and just a word on sort of the history of this result. The hardest part by far is to prove that this gadget is actually an isotopy invariant. And that was essentially proven by Khovanov-Rozansky in this paper, Matrix Factorization and Link Homology, that really started this whole business. I guess, and that was maybe a slightly less general version because they only considered, in the notation we've been doing here, they only looked at W of x equals 1 over n plus 1, x to the n plus 1. But this is the case where you actually have a grading, and what they really wanted to look at was sort of the E2 page of the spectral sequence associated with that filtration. And then you get a doubly graded homology theory that is what they were defining here. And then later on, Rasmussen and Wu both considered sort of the more general version with general potential and set up the story as I've presented it here. And once you have that this gadget is an isotopy invariant, all you need to do to check that we get these filtered chain maps that induce isomorphisms on homology from concordances is, well, you can also write down sort of chain maps between these from not cobordisms. You just need to check that if your cobordism is a concordance, it induces an isomorphism on the homology group. But because the homology group doesn't care about the filtration at all, we can completely forget about the filtration. And now the fact that we were just sort of filtering a mapping cone whose result is that virtual crossing becomes very critical, because when we forget the filtration, suddenly all we're doing is tensoring together that virtual crossing factorization for every crossing over knot diagram, and everything unravels, and it only depends only for the unknot. You only need to check the concordant results for the unknot once you have this isotopy invariance thing set up. Okay, and finally, I want to say that it's often more convenient to look at sort of a reduced version of this homology, because there's kind of a leftover action of Q adjoin X on this whole setup. This is to some degree due to the fact that we imposed that extra relation to every crossing just sort of by fiat instead of letting the differential take care of it for us, although there was a little bit left over in that case. So we can just fix any number A, maybe a rational number, if you want to like change base to the complex numbers and let A be any complex number, and then take a reduced homology by just setting the extra variable, which maybe you have to pick a base point if you're working with a link, to equal that fixed value you set. And now this winds up being very, very concrete, because you get this reduced homology. You can prove that you can write down a chain complex represent, like say homotopy equivalent to that filtered chain complex by starting with the vector space just given by this SLN homology. So in the case W of X equals X cubed, this is just the Khovanov homology, or more generally, it's the Khovanov-Rozansky SLN homology. And then you're going to draw in some differentials that respect these two filtrations given by the quantum grading minus n+1 times the homological grading and just the homological grading. And then this enables, particularly in the case of Khovanov homology of the potential of degree 3, quite a few non-trivial computations and quite a few Fourier invariants you can extract from the setup. I should say that there's kind of, I've written this as depending on the full potential and this number A, but there's actually quite a lot of sort of freedom in those, and that leads to kind of, if you see versions that's written down other places, they're going to different conventions, basically because of that quotient that we took, the constant and linear terms in W kind of aren't going to matter at all, only the quadratic and higher terms. And you can also kind of change your variables by adding a constant in order to make this value A whatever you want. Like the A only, you can change A if you also change the potential in a way to compensate for that. So in the end, you could assume that A equals 0 and that W has only starting with quadratic terms, and then you would get essentially all the same information. So for instance, I think this version of a reduced version of homology quite a lot like this was considered in Loeb, Luer, I think it's called New Quantum Abstraction to Niceness. To sliceness. And there they consider a similar story, but assume that this A is a root of the derivative of W. And that can always be achieved via these, like, by adding, say, an extra linear term to W to make that true. Okay. Right, so it's sort of this invariant that I think is just about the most general reduced invariant that can be extracted from the reduced Khovanov-Rozansky homology that knows concordance information.